I guess, can you share your screen?
Great, yep. Let's see, I haven't done this. Is that, are you seeing it?
There you go, yeah, perfect.
Got it? Okay.
It won't. Oh, yeah, because you didn't really.
Yeah, that's cool. Great. Yeah, Reza and I are really looking forward to hearing more about stress. Actually, we're both kind of stressed.
Wow, this is a great topic to start on then.
Yeah. Cool. So the floor is yours. I'll give you the 10 minutes and then we'll switch it over soon after that. I'll cut you off. I'll let you know when there's a minute or so left.
All right, we're good to go?
Yep.
Cool. So, hi, I'm Maria, and I'm going to talk about developing a voice-based biomarker for stress. So I'm sure we've all felt the negative effects of stress. It's a pretty unavoidable part of daily life, but it actually can become dangerous too, as you see on the bottom here. Chronic stress can lead to all sorts of negative health outcomes and changes in the brain, such as leading to heart disease, heart attack, depression, faster aging, just to name a few. Although I should note that stress isn't always bad. Sometimes it can be very productive and positive. But given its pervasiveness, it's pretty important to study stress and its effects, and in order to come up with solutions, preventions, and to understand it better. So this brings us to the problem of how do we accurately measure stress? The most common and simple method is a questionnaire. You ask people structured questions about how stressed they're feeling, and these are validated and widely used, but they do have some problems with self-report, one of which is, although we can ask people to please tell us the truth, we have no way of knowing whether they actually did. The next best method is biological measures. So for instance, cortisol is a hormone that's released by the body when it's stressed, and you can measure it from your saliva and from your hair, although there are complications with this too in terms of the lab testing and the timing of it. And we use heart rate variability, which is taken from the ECG, and it looks at the variation in time between heartbeats.
Cool.
Sorry, I just wasn't sure if you were talking to me.
No, keep going.
I heard somebody, but I wasn't sure. So both of these measures are more reliable, but they also require more investment, expensive lab equipment, training, and the physical collection of samples. But what if we could gather all this information without anything, just passively listening to someone speak? This would be way more convenient and less expensive for everyone involved. So when we talk about measuring stress from voice, we need to identify which features are changing when someone is stressed. So based on past research, I've identified the features that have been shown to change under stress in more than one study. And in this graphic, the relative size of each feature corresponds to its relative influence on the accuracy of the model. So the fundamental frequency are the biggest one here, because it's known to have the most significant change under stress, as the mean, the variability, and the range all increase when a person is feeling stressed. In contrast, intensity might be not so helpful, because although it does change under stress, it also changes depending on the orientation of the microphone and the speaker's distance away from the microphone. So that may or may not end up being really useful. Other features that are important here are the glottal source spectrum, which changes its slope and its energy distribution. The average formant, location, bandwidth, and variance, which tend to shift into higher frequencies. And the speaking rate also tends to increase when a person is stressed. So the next step here is to gather these into a brilliant SVM model and run some data through them. Although unfortunately, I was not able to find any data. Well, I found some data, but I couldn't have access to it. So this is as far as I've gotten, sadly. But nonetheless, I hope that this will still be useful to you guys and to others in the future. Personally, I think the best way to learn things is when others can benefit from my own learning experience, and that doesn't really happen in my regular classes, so I think this is kind of a cool and unique opportunity, different way to learn things. And it was also a nice first step into the world of neurotechnology. As I'm preparing myself for grad school, I'm currently applying to PhD programs, and I want to develop new neurotechnology as part of my research, so this is really relevant to me. So just want to say thank you for the opportunity and for your support throughout this project, and I'll turn it back to you with any questions you have.
Awesome. Maria, that was great. Reza and I were sitting back, and we've done a lot of work in stress ourselves, at least thought about it. And I think the way you framed all the research is really elegant and super helpful. So really thank you for that. I guess the main question I would have is, as a next step, do you think, like, how would you design a study to get stress samples? Say you could get like a lot of recordings, speech recordings. Mm-hmm. I've thought of things like students before and after an exam. That might be like a pre-stress and then post-stress state, stuff like that. But like, what would be a good control versus stress state experiment you think you could design?
That's a good question. Well, I actually had this really cool data set that I was hoping to use, and unfortunately, I was never able to get access to it. But it was actually a data set that I helped create in research I was involved with a couple years ago, where we gave people a stress task and we were video recording them, and we were taking the biological measures that I mentioned earlier. And so we have voice samples of them with pre and pre-stress and during stress and post-stress, and all of the biological correlates of it.
How many patients were there?
While I was involved, I think we got around 25, but I think there was more after that too.
Yeah, we would love to follow up on that. If you have that data set.
That's what the issue was. We tried to follow up on it, and the faculty moved to another university.
Oh, God.
And you tried reaching them, right, multiple times. And
I've been trying really hard for the last 6 months to get in contact
well, we
with
can make one. So we're launching a NeuroLex product within NeuroLex. And that's something that we might be able to do with our new product. Maybe try it out, get some stress samples, maybe through your score or heart rate variability. We have Fitbits as well for a while ago. So if you want to continue, we can try to make a new data set if that was hard. But that's awesome. That's really sad. It's like that. You got that. That's sweet.
Did you ever figure out at least where the data is stored right now? I mean, is it still WPI, or did it go with the person? Or?
I think she was the only one who had it.
So he just never responded, right?
Yeah, I'm not sure that her WPI emails even work, and I didn't have other contact info for her. And I went to everyone in the department, and no one could get in contact with her.
I'll find her.
Yeah,
I have my ways.
Send me her name again, would you, on Slack maybe? Just send me a private message, and I'll try to track her down.
All right, sure.
I'll pretend I'm the government and I'm doing an audit of funding.
Okay, go for it.
But yeah, I guess we have like 1 minute left. We get your stage. I mean, if you want to continue, we love to try to keep this going. I think stress is an area we built models for stress, but they're very qualitative models, and we don't have objective markers. So I think this is a really awesome area for us, and we'll definitely keep in touch in the future research that we do, and love to try to engage you maybe with some.
I think we can probably get some data. So if you still have some time, like this academic year, I bet we can make this happen.
That would be awesome.
Just to get some models built. Yeah.
Yeah, I'd love to.
Okay, excellent.
Cool.
Thank you.
Thank you so much.
Great, thank you.
Moving on. So I guess I think Haoxin is the next presenter. So I guess
I'm trying to setting up the screen.
Oh yeah, at the bottom you can hit share screen.
There's a green button, like it kind of looks like, yeah, there you go. You can see it. Good. Go ahead.
Do I need to turn on the video camera, or is it okay?
No, it's good. You're good. Whatever.
Okay.
We can see everything you're seeing.
Sorry?
You're good.
Okay.
Where's yours?
So, my project is to detect different English accents, and it's beginning. The problem is that speech recognition has been a part of our daily lives for quite a long time, and we use Siri or Alexa all the time. But one thing I experienced is that I'm not from English speaking country, so sometimes I have to speak to Siri a couple of times for it to understand me. So I know I'm not pronouncing something right, and there's a certain way that Siri has to receive the voice data. So I think pronunciation or accents have an important role in speech recognition, or improve how this system to recognize people's speech. So in this project, I use a simple model of neural network and k-nearest neighbor to perform a binary classification of different accents. So the data there are 16 different English accents from the Common Voice dataset, and including English accents, Hong Kong, South America, and etc. And besides the accents itself, I also put in a control group which consists of a different mix of other accents, and they are randomly chosen as the control group. So we have a binary class of these accents and not these accents. And the data I use is the only features I use are just the MFCC features, which consist of 13 coefficients and data coefficients. And this is just a schematics of how to extract the MFCC. And I used the Librosa library was used, and it was pretty simple to extract the features. And before I feed into the neural network, I combine all the instances into one CSV file. So have the label each instance with its accents, and then all the different features of each instance, which for each accent is a really large array of data. And so for the neural network, for the structure, it's I've tried different using different hidden layers and different nodes, and I realized as I increase the hidden layer and nodes, the model experienced a large amount of overfitting. So I figure, and I realized one hidden layer and 15 nodes are optimal choice, which is really fast to train, not like 10 layers, and also produce a good amount of accuracy. And also use ALT recognition to reduce the overfitting. And the bottom are just some the activation loss function I chose, which is a really common standards. And these are the results of the neural network. As you can see from the table on the left, so, the accuracy are pretty much in the high 70s, which are really not that high, but I think it's good enough for this data set and this accent detection fields. But on the right graph, you can see although the average is around 75, 76, but it's really the accuracy fluctuated a lot. But I really don't know what's going on. Maybe it's the quality of the data sets, the individual quality of the data sets, or something. I should add. There's a better feature I should use. And other things that I use k folds to train the data, which I divide the data into 5 folds, and each time use 4 folds to train the data, and the 1 fold to test the data. So and then average all the accuracies to get the table on the left. And then I use the KNN model, which is the k-nearest neighbor model. This table shows a previous study which has approximate accuracy of high 70s, which is really close to the neural net model. And this is the KNN model I use. The only hyperparameter I get to choose is to change is just the k value, and the k doesn't really change much between 1 and 10, and using 1 is really fast, so there's no point of using 10, and I get similar results. And on the table on the right is the accuracy of the model, and these are really much higher than neural network, and they're really easy to train, and takes really less time too. And one interesting I found is the South Atlantic accents, which has really high accuracy for 91%. Also, you can see in the neural network, it's also really high. It's the highest, 92%. So I'm not sure what's going on. What is special about these accents, or it's just?
I think they just speak a little deeper. It's a lot obvious when you listen to them.
Oh, really? I'm
it's
not really
very different.
Know how they sound differently.
Yeah.
Because
I didn't interrupt.
Because no, that's okay. Because I always assume like Asian accents or Indian accents are more different than the English accent. So I was expecting like Hong Kong or Indian to be really high. So just interesting.
If you look at language features and other different features, you probably find that difference. But since you only look at MFCCs, it's more about the sound in a way, right? And you sound the same as we do if you look at just frequency spectrum.
Mm-hmm. Yeah. Okay.
Same words.
Right.
So what I have learned from the projects, I think the main thing is just confidence. Although I have some training in computer science, but the work I've done is always like assignments, homework, which are just following the steps from the professors. And for this project, I really get to do things on my own with little help. I get a lot of help from my gym, and I'm really thankful. And so through the process, I built a lot of confidence, and I think I can go on to do more difficult tasks and projects on my own too. And the other thing is I get to use online libraries, and get to become skilled on how to choose the library and what kind of what functions to use, where to look at. And another thing is just data processing of how to organize a large amount of data, which is really important for machine learning fields. So for the next step, I'm still continuing exploring other features, preferably sequential features in time series, because I think in order to have a larger improvements, I need to have the model. I have to introduce the history of the model itself into the later training. So the model can learn better, which can be models such as recurrent neural network and HMM models. But I am still having a hard time to organize the data, because each instance has different time series. Some has like 5 seconds, some has 10 seconds, and I have to find a way to extract to normalize each instance and find the most useful information from each instance to feed into the data set, into the model. That's it. That's the reference I use. And
awesome. I think we have a minute. So I guess the only question I have is, what grad school do you really want to get into?
Right now I'm thinking on Columbia and Stanford. It's my top choices.
Awesome. Yeah, because I wrote him a rec letter. I hope you get in, man. I
Yeah,
saw
thanks
the
so much.
ones.
Yeah.
Let me know how else I can help there. But yeah, I
yeah,
think this is great. I'm looking forward to continuing this work and.
Okay, thanks so much.
Awesome, man.
Yeah, great work. Thank you.
All right, so I think we might have a break. No, we have Raj. Okay, Raj, are you there?
How's it going? Can you hear me?
Yes. Hear you great. I guess Haoxin, can you stop sharing your screen? I think you can somewhere.
At the bottom, you can say stop sharing. And then Raj can share his screen.
Let's do that.
And so do I press record?
You don't have to press record. At the bottom, there's a green button that says share screen.
Okay,
I think Haoxin has to get rid of it. Haoxin, did you stop your screen share? I think I have to get rid of it. Yeah, so in 1 second, I'm gonna figure this out.
You can just
put on hold. All right, I'm gonna remove you, Haoxin. If you can join back in if you want. All right, now you can join. I just kicked him out, so hopefully he doesn't hate me for that. But now it's this green button down there. Yeah, perfect.
All right, can you see it?
Yep, see it perfectly.
All right, hi guys, my name is Raj, and my project's going to be about analyzing voice samples to predict age. So the problem is basically, as the title might, allude to, is knowing the age range of the individual based on their actual voice sample. So this is based on like whether they're in their teens or their 20s or their 30s, and there's actually 8 different categories. It goes up to 80s. And there's 2 main reasons why, solving this problem can be useful. The first is that knowing the age range can help us predict what disease it is. So if you can see like the picture of schizophrenia on the right. So typically for females, the onset of schizophrenia is like after age 30, while as with males, it's like from 18 to 25. So if you know that it's a female in their teens, that that they're probably not gonna have schizophrenia. So that's just an example of how it can be useful to predict the nature of a disease. And the second main reason is that can help you get specialized care based on, let's say someone has depression. If care for depression with someone in their teens is going to look very different from someone in their 50s. I mean, whether that be the therapy that they're going through or the medicine that they're taking. So those are, I would say, 2 big reasons why solving this problem is useful. So the data set that I used was the Common Voice data set. It has about 200,000 samples, but only 73,000 are actually labeled with age. So I had to basically settle for that in terms of training my data. And I use Pi audio analysis for feature extraction. So that has about like 34 features, and I basically took the min, max, standard deviation, average, and median for each one. So that ended up 34 times 5 is like about 170 features. So my initial approach was just like a normal neural network, a normal multi-layer perceptron, 5 layers with those dimensions that you see on the screen. And I used a support vector machine for feature selection, and that got the features from 170 down to 81. And the accuracy was about 70.7%. So there was a little bit of overfitting because, the training accuracy was about 74%. And I thought there were a couple problems. I thought there was some overfitting, and I didn't think the accuracy was particularly high. So I tried another approach, which was actually turning the audio file into an image class. So essentially turning the problem into an image classification problem. To do this, we had to convert the audio into a MEL spectrogram. So typically when you have an image, right, you have one axis as the width and one axis as the height. And then the actual values, let's say you're dealing with a grayscale image, you're talking about, if it's closer to 1, it's a darker pixel. So in this case, one axis was time and one axis is frequency, and the actual values are the amplitude of the wave at that particular time. And I basically got this. There's a lot of approaches like this online, so I thought it would be, cool to actually try this approach rather than just a normal multi-layer perceptron. So unfortunately, there were very low accuracies when I tried a 2D convolutional neural network, as you know, that's the typical approach for an image classification problem. And I got very low accuracies, probably like 26, 27%. And the training times were just like ridiculously high. They were getting up to like 1 to 2 hours. And so I wanted to try and use a pre-trained model in Keras, but the problem with that is that you actually need 3 quote unquote channels. And so in this case, so it's typically used for image classification, and they're actually typically used for color images. And so the channels are basically referring to 3 channels are basically referring to RGB values, so red, blue, and green. And obviously that didn't really have an application in this case. There weren't 3 channels. So I couldn't actually use those pre-trained Keras models. And so I put that you might need a GPU because that's something that definitely speeds up the training time. So, you know, because those training times were so long, it was kind of hard to actually fine tune my model because I didn't really know what the accuracy at the end of the training time was going to be. So I just tried to adjust my multi-layer perceptron a little more. I did about 50 epochs before, and then this time I tried 100 epochs, and the training accuracy went up about 7%, but the testing accuracy only went up about like 2.3%. So it's still kind of an overfit model. So I think there's definitely going to need to be some more exploration in terms of different approaches to get a higher accuracy. In terms of the impact this has had on me, I would say like all the stuff I've learned regarding deep learning has been through this project, which has been like awesome for me, like being able to actually do a real project, especially something as complex as dealing with audio data. And like through that, I also learned a lot about signal processing. And I sort of saw, like when I first heard NeuroLex was like, hey, they like analyze voice samples, like I was like, how does that even happen? Like, how does that even relate to data science? And so I was able to actually see like, hey, this is how they process a signal and turn this into data and actually be able to run models through it. In terms of my next steps, I would say that, so I'm actually doing this as part of a capstone project for an intensive data science bootcamp. So I'm going to be like going a lot more in depth. I'm going to be trying like more architectures. I'm going to be learning more about the theory of deep learning, why certain models might work for my particular problem. So I use Keras. I'm going to probably re-implement it in TensorFlow to, get a little bit more control and fine tuning the parameters. And I'm going to be writing a lot more detailed of reports on this project. So yeah.
Awesome, Raj. That was great. And yeah, I think age is a hard problem, and I think getting the images right for a CNN or an RNN, mostly CNN, is often really difficult with images because it's not like a typical image where you have like a face or hands or feet.
Right.
You do semantic segmentation. It's a lot of randomness and noise profiles are different. So there's a lot of factors that make spectrograms harder to work with than images.
Yeah.
I think. But yeah, I think it's awesome you tried those approaches. Some of them we looked at, and I think the accuracy is pretty good for a first start. It's a hard problem. Age in general. But just the real question I had was like, was this the way you separated the classes? Was that the multi-layer perceptron you trained across all ages as predicting like an output class of the age, or were there independent models you trained as well, say to predict like teens or 20s or 30s independently?
So I trained all of it in one, I believe. Yeah, I trained all 8 at one. Okay,
cool. Yeah, so that's pretty useful then, because I feel like right now, if you think about it, that's probably like, relative to chance, that's probably like 3 or 4x chance.
Yep.
So it's pretty good, just by that metric. But yeah, I don't know. I'd love to like if you have your code, if you want to write a research paper too on this, is something that like Reza was talking about in our lab. Like we've been trying to publish more papers in IEEE and some of the journals. So if you want to take some of this work and publish on it, this is another option as well if you're interested.
What is the course you're going to use it for your capstone?
So it's called, it's for this company called Springboard. And I basically started the boot camp around beginning of June. And so there's two main capstone projects. And the second one I chose to focus on deep learning. And given that I was, doing this project, I know that you said like in your FAQ that the age detection was like a deep learning approach would be useful. So I thought it would be a good opportunity to sort of combine the two, like kill two birds with one stone.
Yeah, let's try to, I mean, if it helps you too, I mean, I think this could be a nice paper, nothing crazy, but a nice short paper, scientific article, and we can publish it open source, so you can see it.
Yeah, for sure.
That sounds like a good idea. Cool.
Awesome. So I guess we Tarun, are you there? I don't know. We have a little bit of a break, but if you want to present in a second, you can give us a few like a minute. Grace is going to the bathroom. Yeah, it's a good start. I'm excited to hear the rest of your guys' pitches. It's always fun. And I think demo days are always fun to recap everything. But yeah, I'll let you know. Give us like a minute. I'll ping you to share your screen. Everything. Keep recording. Huh?
The redesign was survey.
Good. Finally, we needed that, right? Like you saw how that was. I think Marcel being in there as an independent voice is really good.
Yeah, because he has a lot of projects for this, which is nice. Yeah. What's the schedule for tomorrow? Team building?
Yeah. Tarun, you can start. We're here.
Okay. So, hey, my name is Tarun, and what I worked on, it was like more of a concept for a software demo. And the software demo is on essentially test the effect of stress on articulation. So the premise of this issue is that stress has effect on many different facets of a human. And one of these facets is articulation, as people who are more stressed are unable to think properly and therefore can't articulate their thoughts well. So this arises the question of how can we measure this? And therefore the research question being asked is, how does stress affect a person's articulation, and how can we measure using feature extraction of repeated words or pauses? The concept of this will be based in Python, but some libraries will be in C. The word features tested will be the number of pauses and repeated words. And the two situations will be without a stressor as the control and with the stressor. And there will be three different stressors that are tested, which are disaster, which includes like a fire alarm, academic before after a test, and social, which is after an argument with, say, friends. So the hypothesis is that for this experiment, it's a count of either the pauses or the repeat words. If either of those counts increases, then the level of the stress will be higher based on the threshold set forth. So the data set used in theory, so I wasn't able to really grab a data set, but in theory, the data set will be divided into two sections, samples with no stressors and samples with stressors. And the stressors will be divided into three different categories, which are, as mentioned before, disaster, academic, and social. So for the algorithm of actually getting this feature extraction, first it will be like counting the number and length of pauses or number of repeated words. And to determine the frequencies of certain words, the Natural Language Toolkit library, using the freq_this model, will be used to determine the frequencies of certain words. For pauses, it will be used the feature struct module. And then the counts of both pauses and certain words will be determined. And based on the number, the amount of counts, the higher count will be used as the deciding factor. And the count that will be then the count that's used will be compared with different thresholds of stress that are based on previous data. So to account for the length of pause that I am using, if I use the count for the number of pauses, then I'll also use the length of pauses as a factor in determining the level of stress. And to assist this process, the support vector machine will be used to determine a relationship between the counts of either the pauses or repeated words and the different stress levels. So from my literature review, I was able to find some articles that really pinpointed and really gave a basis into what I want to accomplish. One is like multimodal speech recognition with audio artifacts. So with this methodology, I can use it as a basis to use multiple frames to locate the pauses in an audio sample better. And then another article I found was detection of articulation disorders using the support vector machines. So, and based on the use of the support vector machine, I can implement that machine learning algorithm to determine, because in this scenario, it was used for sounds. So I can translate that to determine different words, as the syllables will be determined factors. And then expanding on that, I plan to use a brain-computer interface to understand how the signals in the brain correspond to the different problems with articulation. So the article on brain-computer interfaces for communication and control, I can use that methodology to test the neuron activity and compare it to the word count to the pause counts. So in conclusion, while there are no results so far, the developed program device will theoretically be able to detect an instance of stress based on articulation patterns. And it will be useful, especially with people dealing with PTSD and other stress disorders, because they'll be in situations where they'll be impaired to speak in the stressful situations described earlier. And with future plans, it'll be implementing and testing a simple algorithm that tests pauses, then add functionality to detect the repetition of certain words, and then within a year, use brain-computer interface to determine the relationship between neuron activation and patterns of pauses and repeated words. So the effect on my career, I definitely want to now more integrate machine learning and more embedded hardware, so I can create like better devices and understand how to implement. I now have a better understanding of how to implement computer science into healthcare.
Awesome, man. Thanks for that presentation. I think, I guess the real question would be, like, over the next 3-6 months, what do you think is like a reasonable goal for, say, a pilot, like in terms of number of subjects or how you go about getting the data? Because we do have a SurveyLex product in NeuroLex now that we can get data easily through voice surveys. It might be cool to implement this SurveyLex product to get some labeled data in stress, either in the university or some workers. So just curious your thoughts on that.
Okay, so I've seen more of I could have like 8 subjects, and all the subjects go through the control and the three stress scenarios.
Okay, so you just get a few people and just look for patterns, and do you think 8's enough?
I think I could start out with 8, and if I need more data, I can definitely increase the number.
Cool. All right. Yeah. So that's cool. I think the other side of it too is I thought the idea behind disasters, disasters in particular, like natural disasters, was actually pretty interesting. Do you think there's like YouTube data out there that shows like a family or a person before and after losing their house or like losing a loved one that would indicate a stressed versus unstressed state as a control, as potentially as an alternative source of data to train on?
Well, I have watched certain movies where there have been like the characters were like stressed like much more after losing their house to like a hurricane. So I'm sure there's like YouTube videos out there that definitely like document, because there's YouTube should have like news reports and people's like interviews, news interviews. So I think there will be some data on that.
Yeah, it might be a good place to focus then, because there's probably a lot more data, would just be my quick thought. Like you might be able to get like 100 YouTube samples in a stress state versus 100 an unstressed state. And I'm sure there's a lot of interviews from news anchors or whatever. So let's talk offline about that. I like that idea. It was kind of intriguing. I didn't really think of it that way before. But yeah, I guess that's it. Ray, any questions?
Yeah, I would say, because you did a really nice job theoretically setting this up and having your hypotheses ahead of time, which often with machine learning work you tend not to do, is just kind of jump into data analysis. So it'd be nice to move this ahead and get some data for you. And one of our previous tribe members has some stress data from PTSD from veterans in Houston, David Mathai. So you might want to message him. He's on Slack. I'll give him a message, David Mathai.
Okay, yeah, I'll definitely give him a message.
Okay.
Cool. Well, we're going to take a quick break. We will be back at 3:20. I'm going to pull up my screen. I'm going to pause the recording. Okay. Dylan and David.
Yep. How's it going?
Good, man. Both of you. I actually just talked with Paul. I'm super excited to hear what you guys are working on. So
Sweet.
So feel free to share whenever. I'm going to take my screen off. I'm with Reza right here. And the product team, just so you know, you guys know that we broke off from the core product team. The product team's kind of doing a hackathon, but we're recording all these presentations, so we'll definitely get feedback from them at a future date, potentially.
Okay.
All right, cool.
Cool, so I'll let you guys go. I'm gonna mute and just listen.
All right, we're gonna kind of go through it pretty fast to leave time for a question.
Sounds great.
So tentative title, Effectron. This is the project we've been working on. So the problem we want to solve is that it's difficult for patients to objectively gauge their mood and communicate it to their doctor. And this problem is compounded when considering the often lengthy time between doctor visits. You'll often hear a doctor say, come back in a month and tell me how it worked. And that's really difficult to do whenever especially if you take some kind of medicine that's supposed to alter your mental state. The effects are subtle, and it's just a lot to ask somebody to accurately evaluate how a medicine worked, especially if they're taking multiple at a time. Lots of variables, and it's messy. So we want to solve that. We want to create an easy-to-use web application that helps patients and medical professionals evaluate how different medications affect a patient's mood. The application should act as a log and allow the user to store medication and mood data to allow for easy correlation between their medications and their mood over time. The application should also present the collected data via an easy-to-understand visual representation. So the features are a list of current medications and doses can be entered into the app. Changes in medication can be recorded and updated at any time. Patients can create a log or can create log entries that include a short voice sample. And this is where NeuroLex comes in. The voice samples can be evaluated by NeuroLex's API, and the resulting mood analysis can be stored with that log entry. Mood is the feature we're focusing on now, but as more features become relevant, probably a lot of things that can be detected in voice can be relevant to someone in this situation where they're trying to evaluate medication. So we're just saying mood now, but any of those features could be relevant. The resulting visualization will show the relationship between mood and medication over time. And the outcomes we want are that when patients discuss their treatment plans with healthcare providers, their decisions will benefit from solid data about how the medications have affected them. The ease of use will allow for a higher frequency of data collection because they can do this every day or multiple times a day. And since it's not self-reporting, they'll have a lot more objective analysis and like hard data to show their physician. It'll give them like a more clear view of what's actually being affected. And these outcomes ultimately lead to better informed decisions about continuing or modifying the patient's treatment plan. So next steps are, make a product, iterate a few times, get this out there in the world, get some feedback from healthcare professionals, and hopefully launch it as a product. So I'm going to go through the application flow for the NeuroLex integration part, because this is what's relevant to you guys. The rest of it's just kind of housekeeping stuff. So step 1, user uploads a sound file and kicks off 2 events. 1, the sound file itself is sent off for processing, which is one route that I'll get into. And number 2 is we simultaneously create an entry in our database associated with that user. So when the analysis comes back, the results for that will be linked to the entry we've already created. Since it's kind of an asynchronous thing where NeuroLex is independently processing, we just need the return to associate the entry that's already been created with the analysis. Once the sound file's upload is complete, S3 invokes a Lambda operation that sends the file to the NeuroLex API for analysis. And once it's complete, it'll trigger an alarm or something to run another Lambda function, which writes the resulting analysis back to that entry we talked about earlier in the database. And then from there, the web application will have this live data. I mean, I don't know how long it'll take NeuroLex to analyze it, but even if it takes a long time, we'll keep the web application have automatically updated data. So when the process is done, the user will be able to see exactly how that correlates. And I'm going to hand it over to David now because he's going to show you the interface we have. It's a work in progress, but the elements are there.
Cool. All right.
Awesome. Yeah, that looks pretty interesting. Medication dosing and compliance are one of the things that we've been looking at in our research. So I think some of this could be super cool. But you keep going. I didn't mean to interrupt.
No worries. Can you guys see my screen? Can you see?
Yep.
Okay. Awesome. Yeah. So this is just a quick overview of the UI we have so far. Some of it works, some of it doesn't. We're still looking into what the best visual representation would be. So right now you can see we have mood score on the side here, time on the bottom, and we have Zoloft and Adderall represented by the blue and green lines on the graph. And you can see during the, and no medications as well with the red. So you can see during the no medication portion of time.
That's a bug.
Yeah. That the mood fluctuation was pretty great. Sometimes there'd be some highs and lows, but when it got on Zoloft, it smoothed out a little bit. And on Adderall, you can see it's still smoother, but their mood is overall better. So this gives just an easy way for a user to say like, hey, apparently I feel better on Adderall.
Is this with real data or is it?
No, this is just made up data.
I figured it was data. Yeah, but it's cool.
The ideal application.
From personal experience with Adderall.
Yeah. I
personal.
take Adderall.
Yeah, anecdotal data would say.
But just if there was a correlation this clear, this is the perfect application of this kind of visualization.
Yeah. So we're still trying to figure out the best. We'll probably have to do something a little more custom. This is just like a chart.js thing right here. We'll probably have to build something a little more custom to get exactly what we want.
Because we're not demonstrating layers of medication right there in case they're overlapped, and that's going to be a big feature. But that's just something trivial we'll be able to fix in a short amount of time once we decide to the graph
Yeah.
library.
So we have, and then we'll just have a form to add medications. You can add them. You can actually do something. I don't know what that would be. And yeah,
That's kind of cool.
add it up there, and then you can do the same thing files, and these are kind of like separate. So this would update the graph in a perfect world, but here it doesn't. And yeah, we have files where you just do that. The user can see the files, they can play, pause, and stop them, and we'll have the future ways to edit, your medications, or maybe even like make a whole treatment plan so you can track it by treatment plan versus individual medications. Either or, I think that'd be a nice feature for the user. But that is pretty much it for the UI there. But yeah, yes. So we're open to questions now.
That's very nice.
Yeah,
that's pretty cool.
Yeah, I think the visualization is really awesome. Like separating it out with bands of colors and audio features or whatever mood score you're using. It's kind of cool.
Have you guys looked at other companies' little apps that are trying to do stuff like this?
We've just looked at a couple of them. I don't remember the names, but no big research.
Like Mood Diary. Yeah, I mean, the visualization you made is nice. I haven't seen something this like kind of nice and I don't know, just easy to process. But there's a bunch of other apps out there, and it's worth exploring further. But words of caution too. Like building up apps that are tracking. Like, what's the end goal? What's it helping with? It's hard because you're ultimately using subjective data. You're just presenting it in a nicer way visually, but you're asking patients how are their moods. You're capturing the nice objective data about whether or not they're taking medication, what dose, which is great. But in terms of measuring mood, I like the NeuroLex integration because we can add voice features, which is a little more objective.
Yeah.
You know what I mean? Just in terms of asking them how they're doing, that still leaves it subjective. And so like the graphs will tend to be obviously all over the place.
Yeah, really a fully featured thing would have probably a bunch of different kind of graphs to really tease apart the data a little more, and maybe some more, not just such a linear like 0 to 100, like sad, happy,
Right. If you look at, there's other groups trying to track like movement data, walks, steps per day, GPS, and like integrate all this into like kind of a mood. Into the mood diary, so you can see other data points too. Voice would be another one. But.
Yeah, this right here is not like necessarily a perfect tool, but it's definitely going to provide a benefit to the healthcare provider, because now, there's no objective criteria. You're just like, hey, they ask you if it worked, and you just say, yeah, I guess so. I kind of feel good. So, at least if the interface is simple enough to where they can consistently upload data without trying to like kind of spin it in their mind and, obfuscate it by condensing it down to one word. That level of granularity will be good. And the fact that we're using like a third party thing to evaluate the voice sample, that's a little bit harder to manipulate than somebody just trying to tell you their mood.
Yeah, and I think like one thing we could do is we made a PHQ-9 regression model. It might be cool to tie in that regression model to some real life data in a research context to get live data into this. So we have a regression model that can estimate the PHQ-9 output score, which is similar to mood for depression. Like the higher the score, the more depressed they are? Yeah. So the higher the score, the more depressed they are, the lower the more controlled they are. So that could be really cool to see the effect of an antidepressant.
Yeah.
Over time. The biggest concern I have is a compliance of the user and making sure that people use whatever you put in front of them. I think that's always hard, having patients comply with anything new.
Yeah. Oh, for sure.
But I think kind of ABC testing that relative to other things would probably be good to say, hey, maybe we have like 200% more engagement relative to other apps or everything else.
Yeah.
For sure. I think a core focus for us would be to make the interface as seamless and easy to use as possible, so people don't have to, learn, like, read a manual.
Yeah. We don't want to make them think. We just want to let them use it.
Totally. So yeah, just some comments. So what do you guys want to do next with this? Do you think that I think we're running close on time. Yeah, I'll stop you because we have to keep going. But yeah, great job, guys. I think this is an awesome interface, and I'd love to stay in touch and see how we can work together on various projects concurrently.
Yeah, absolutely.
Cool. Yep, definitely.
Cool.
Nice
Appreciate
work.
it. Thank you.
Thank you.
Yeah, thanks.
All right, so we're gonna go to Kathleen. Are you there, Kathleen? Kathleen Williams. Okay, yeah, you're there. You want to share your screen?
Yeah, so we're showing my screen.
At the bottom, you see the green
there's
button?
there's a green button down there.
Oh, I see it. Okay, cool. Okay.
Awesome.
Yep. And okay, so my research is a longitudinal study of seasonal affective disorder in female YouTubers. And the purpose is to verify if pitch would be an accurate indicator of seasonal affective disorder when compared throughout the different seasons. And pitch variability has been shown in different studies to be an identifier of psychomotor retardation, which is a common symptom of depression and affective disorders. And statistics have shown that seasonal affective disorder is most prevalent with women between ages 18 and 30. And 90% are affected during the cold months. And we also want to test the validity of the last bullet point of 10 to 20% of recurring depression following a seasonal pattern, because in my sample, I'm just using depressed individuals, not just ones with seasonal affective disorder. And we want to see if the last statement is still true when looking at the pitch variability. So for preparation, when looking at the statistics on the last slide, the sample will consist of all females and between ages 18 and 30, so that way we have a larger data set. And we want to have enough data for each individual to create a baseline, so there will be at least 4 with 1 during each season. And the hypothesis is that the overall pitch variability will be smaller and the pitch will be lower in the fall and winter months compared to spring and summer. And then for obtaining the audio samples, I'm from YouTube, and they are 30 seconds. For the depressed sample, they were found by searching Depression My Story. And for the not depressed control sample, searched A Day in My Life, and then looking through their past videos and social media and other references online to check if there's any potential depression, and if there is, and they would not be used in the control. For technology, we're going to be using OpenSmile and Librosa. Python was also used for collecting the audio samples, which has already been done for the depressed group. And we're going to be using the OpenSmile and Librosa for getting the mean, the quartile range, standard deviation, and etc. And then the plan of action is, because affective disorders tend to have varying effects from person to person, we want to first compare the individual's results in each season to kind of get a baseline for each one themselves to see if they follow a trend. And then we're going to combine all the data of the depressed group, and then we're going to combine all the data of the control group, see if there's any baseline within those 2 models. And then we're going to combine the 2 to see if there's any overlapping, and if there's a way to distinguish the control and the depressed group from each other. And then for modeling, it's going to be a scatter plot for each individual's average pitch. And it's going to it's going to have all like the depressed group in one and all the control group in the other. And the scatter plot will be used for noticing each individual's average, while the histogram is going to be an average of everyone in that sample's average and comparing them in each season. And then for impact, for me, this was like a big opportunity because I've never done research before. I've also never used Python, so I've been teaching myself Python these past few months. And like my also main career goal is to do neural engineering, specifically with finding more concrete ways to diagnose mental illnesses. So this was like a big deal for me, especially with only being a sophomore in college for undergrad. And for NeuroLex, I think that this research would help with the voice test, because then it will have like a way to like look at how season has an effect on depressed versus non-depressed individuals, and if that is a characteristic to look at when trying to diagnose. Yeah.
Awesome. Great job. So I think Ray's had a quick question.
Did you have any luck finding data on YouTube to support this?
Any what?
Did you have any luck finding data on YouTube?
Yes, I have, let me check how many I have for, because I've already made the voice, the audio for the depressed group. I'll find how many I have.
So you have depressed audio data, and I mean, do you have ones of like specifically of women with like seasonal affective? I mean, how are you getting the seasonal affective data?
I'm mainly just doing depression and just seeing like if there is a trend of season in people with just depression. Like I don't have them really separated.
Okay. So you'll kind of just do it based on when it was posted, I guess?
Yeah.
Because in terms of timeline, how are you going to know what time of year and everything?
Oh, for time, like I'm doing just like one consecutive year for each like YouTuber, and getting like I'm gonna have at least one sample for fall, one sample for spring, summer.
Okay. Just based on when they're posting stuff.
Yeah, like it's going to be, so once I find, also I have 11 videos so far, like sample, like with different YouTubers, but how I'm going to do it is find their depression, my story, and then with like the year that they posted that video, I'm going to get from that year the audio from the other videos in the different seasons, if that makes sense.
Yeah, I mean, what's your goal, I guess, in terms of numbers then? How much data are you looking for?
Kind of like I just want to get at least 4 for each YouTuber, and if I have like time to get more, then I'll.
How many YouTubers though?
How many YouTubers? So far I have 11 for depression, and so I'm gonna find 11 for control.
I see. So you want to do like 11 and 11 and see if you find something.
Right.
Also be careful about, because if you're doing it based on when they post it, right? Sometimes they don't post the videos when it was actually recorded.
True.
You just want to be careful. Like if it's someone that's posting frequently and it seems to do like a lot of live stuff, maybe it's more reliable. But if it's someone that's infrequently posting, yeah, they might be posting stuff from like the past or whatever, or duplications.
But it's a problem. I mean, I think I like the approach. I think that's a really cool, novel view of it. Though I haven't seen many time series YouTube analysis ideas, so I kind of like that. It's a really interesting perspective on it, for sure. Cool. I guess next steps. Do you want to continue doing that, and then maybe do you need help on the data science side to help featurize stuff, or have you already done some of that Python?
I do plan on like working on this after demo day, and Larry has been helping me with like learning the code stuff since I'm still going along with learning the Python.
Awesome. Okay, well, sounds good.
Keep us updated then, okay? Because I want to see what you end up getting for results.
Okay, sounds good. Thank you.
Awesome. Cool. Well, Justin, John, and Annie, I see you guys are on there. We do have a little bit of a break, but if you guys want to go, you can go now if you're ready, or in a little bit. Up to you guys.
Hey.
Yeah, we can do it now.
Okay, cool. Sounds good.
Share screen. Let me just. Can you guys see that?
Yeah, see it great.
Okay. All right. Our project was on collecting voice data from children with autism spectrum disorders. So the problem is that ASD is a very common. It's like the diagnosis rate is increasing. Now it's up to 1 in 88 children in the US are diagnosed. It's a developmental disorder. I'm going to go into the symptoms in the next slide. It's incurable, and some treatments, and the most accepted treatments are like behavioral and speech therapy, as well as medication for comorbid disorders like seizures and ADHD. The importance of developing this diagnostic tool is because minority families, their children are often undiagnosed, especially if they're Hispanic or African American. And also, males are diagnosed at a much higher rate than females because the disease manifests a little differently in females. And so, like I said, autism is a developmental disability, sometimes accompanied by intellectual disability, which can impact like learning in school or living independently as an adult.
Are you guys presenting your slides right now? Because it's not advancing.
It should be on the symptoms and diagnosis.
Okay,
I don't see. Yeah, I don't see it. Okay, cool. There you go. Yeah. Now I can see you shifting. Yeah, maybe.
But if you want to put in presenter mode, then maybe it'll work better. Just hit the present in the top right.
Okay.
Yeah, sorry. I was just wondering if you're advancing, if it was on our end.
Can you see this one?
No.
Okay, that's so weird. Okay.
Yeah, just advance it like manually, I guess. Sorry about that.
Sorry. Yeah, so the most important symptoms are difficulties in social interaction, communication, repetitive behaviors, and restricted interests. So obviously what we're most focused on is difficulties in communication. At least half of ASD population shows like flat or monotonous tone, and in terms of syntax, they repeat words that they recently learned that's called echolalia. They use pronoun reversal, which is saying you instead of I, and also poor grammar. And right now, the CDC recommends screening at 18 and 24 months. So the disease can be detected relatively early. The current screening tools are pretty accurate right now, but they could take up to 2.5 hours.
All right, so I'll go through, I guess, the voice analysis tool solution that with NeuroLex are proposing. So as a non-invasive marker, we thought there are benefits of using voice analysis, such as early diagnosis and avoiding the hindrance of the communication, the mystery on communication cues. As Annie mentioned, children with autism spectrum disorders, they do have difficulty in communicating, and then because of that, there is negative social judgment from their peers. So with this tool, it could prevent social withdrawal and anxiety of these affected individuals. And so the journal that compiled 34 articles on studies quantifying acoustic features and voice in ASD patients. So just looking at that table, it did a study similar to what we're proposing or planning to do, in which it compares ASD individuals to the typically developing comparison group. So, and the goal of using this is to collect the voice samples and also connect these individuals, the affected individuals, with resources such as support groups, as well as referring them to psychologists or neurologists in order to facilitate diagnosis. And so we did submit an IRB proposal, the Institutional Review Board. So at UT Dallas, through our Kathleen Center, which provides evaluations for children with speech disorders and offers speech and language therapy. So by partnering with them, they would be providing the demographics and participants for the study. And so when we submitted the form, we were asking for 100 children from 3 to 10 years old, and doing a similar study structure to the previous side of the table, with 50 ASD children, as well as 50 control group, typically developing comparison group. And the goal is, because I guess we don't have a strong background in programming, or at least with data science, we were wanting to collaborate with the data science team so they could use machine learning meta-analysis and combine that data from the different studies and different trials when we do this, in order to optimize the concurrent audio models that we have. And personal goals, for me, it's to apply to medical school, as well as complete internships in the healthcare sector, whether it's neuro-related or healthcare management, as well as continue to be involved in NeuroLex.
And my personal goals are to apply for internships in like healthcare consulting, or possibly doing research at like an RAU at a university next summer. I'd like to continue project involvement, and I've also talked to a UT Dallas student who just applied to NeuroLex about what the program is about and what the work is like. And I'd also like to improve my coding skills.
And that's just a citation of the study, the journal article that we got the table from, as well as all these ideas to how to structure our trials.
Awesome, guys. Really great job. I think you guys laid out the feature sets for autism really well. It falls in line with the research we've seen before. The biggest challenge with prior tribe projects in autism has been data. So in you guys kind of advancing an IRB study and going forward with it, I think it's a pretty big deal for getting more data and trying to publish a paper. So we definitely would love to stay in touch. And also, we have a few prior tribe members that were at the University of Michigan, at Aditi, and also Georgia Tech, actually Wake Forest and Georgia Tech, that were working in autism. So that might be an area that we could kind of extend this work as well. But yeah, Reza, do you have any questions?
Yeah. So where's the timeline for the IRB, and if we're getting some of that data? This is going to be prospective collection. I mean, you start to do the data collection.
So we just applied for the IRB, and because at the university, because they're working with the Kathleen Center, it might take a few months to get processed. But we also are looking at collaborating with nonprofit groups as well that cater to a lot of the neurological disorders. So it really depends on how fast we can get the IRB approved.
And you're going to add on to a study, or is that to access data that's already there? Do they already have voice?
It's to basically initiate the study, and then with the article that we referred to, it did have a similar structure, but they did it quite extensively with a typically developing comparison group. So we might go in that direction as well.
Yeah, we've had good luck adding on to studies. So just getting your work out there locally, people will be interested because it's so cheap. It's essentially trivial for them to add voice collection to their study, and it gives them so much more data.
Yeah. And we have a product now on NeuroLex called SurveyLex, and we've been trying to do our open beta starting in November 1st. So if you guys get the IRB approved, we can use that product to quickly create a survey for you guys to get data in clinic. Have you guys thought of the voice task to collect the data from the autism patients? Because I'm assuming they're obviously high functioning verbal autism.
Yes. So we were thinking of, there are like 3 categories that we're thinking of, like when we collect the voice samples, whether it's, the first one was constrained production, where it would just simply be the given task is to read aloud. And so we'd be testing just for speech production rather than the content.
Okay.
And the next one would be spontaneous production, where it would be open-ended, so they can pretty much like storytelling in a sense, where it's more abstract, and that would be more content focused. And then the third one would be social interaction, where it's spontaneous and somewhat planned conversations, and that's just a test for the interpersonal and skills as well as social factors.
Yeah, it's really interesting. I think the social one is interesting. Like, how would you automate the social questions about empathy or even just connecting? Or
you could actually give them little brief snippets of like a story and just and then record their reaction to it. Like, what do you think? Like, Tommy was walking down the street and he was walking his dog, and his dog got hit by a car. Tommy's really sad. If depending on the age, right? Make it age appropriate, and then see how they respond.
Yes.
I mean, I think the kid might be like, "What color was Tommy's leash?" Or whatever.
Yeah, like something really specific. But cool, guys. Well, yeah, thanks for all this really great work. Like I said, let's follow up and let's try to advance this. And I think if you get pilot data in the IRB, we can extend it to a larger study, like Autism Speaks. I've spoke to Autism Speaks at the global level, and they have like 10,000 patients in all their sites. So if you guys get good pilot data, we can then kind of like expand it to larger studies. It's just been hard to get the first trial going. So you guys have done a great job just pursuing IRB and framing it for sure.
Thank you so much for the opportunity. Really appreciate it.
Yeah, stick with it and let us know how it works out.
Will do. Thank you so much.
Thank you.
Thank you, guys. Then I guess Kamilah, I don't know if Kamilah is on there.
And just hit stop share at the bottom of your screen. And then
cool, thanks. Kamilah, are you there? I know it's a little earlier than your time. We can wait a little bit.
Is that the last one?
Yeah, she's.
Hello. Yeah, I'm here.
Cool. Do you want to present now, or do you want to wait a little bit? Are you ready?
Can you give me about 5 minutes?
Yeah, no worries. Yeah, we'll wait. I'm gonna pause the recording.
We'll pause recording. Screensaver, the cover of Jim's book.
Oh yeah. I saw you guys walk away and put that.
It's kind of funny. Sorry, we like eat in between.
Oh no, I just ate. It's fine.
I forget to eat all the time.
Yeah, I did that yesterday. Like, I've been trying to eat more fruits, and then I forgot, because when you eat a lot, like, it's like you can't like remember to eat like anything other than fruit.
No, but you don't appreciate it at your age. When you get to my age, eating a lot of fruits and vegetables, you have great poops, which is very appreciated.
Yeah.
You can't take that for granted.
Reza really likes to talk about poop because he wrote a bunch of papers on microbiome and stuff.
Oh yeah?
I think it was a book chapter, or was it?
Yeah.
Pretty cool.
That's all. I see a lot of Parkinson's patients, right? And they're all constipated. So I tell them all to eat fruit.
Wow. Why are they constipated?
It seems to be part of the disease, actually. And some people now think it's actually maybe one of the early causes of the disease, because when you talk to those people, it turns out they've been constipated for like 20 years before they got Parkinson's. And they're finding that the bacteria in the gut of Parkinson's people is actually different than the bacteria in the gut of healthy people.
Wow.
Yeah, interesting. Yeah, because they always thought it was part of the disease, but now people are realizing, wait a second, maybe it's actually causing. It's an early sign.
Wow.
Oh.
So,
and my heart goes out to them.
Wow. So keep eating your fruits.
Yeah, keep eating them. Kind of funny.
Okay, you can start wherever you want.
Yeah, start wherever.
Right. Can you see my screen?
Yep, we can see it.
Cool. Okay, so the title of my presentation is Using Formant Analysis to Diagnose Trauma Disorders. The overview of my project is I cycled through like a lot of different ideas, and I settled on using voice analysis to calculate Formant frequencies of vocal samples of specifically PTSD anxiety and depression patients because they're all related disorders, they're related to trauma. And I wanted to see what exactly sets them apart, vocally. So I decided to implement a program in Python to carry out my hypothesis, which is that the depression samples will have lower frequencies. PTSD will have the highest because of past research on schizophrenia patients by Thomas Bailey, one of Paul Prey's friends. And his research showed that schizophrenia patients have lower frequencies during negative symptoms, like apathy, lack of emotion, and poor non-existent social functioning, and higher frequencies during positive symptoms like hallucinations, delusions, racing thoughts. And also, I found information that shows that anxiety and PTSD are closely related. PTSD is also an anxiety disorder. So it's just, from what I saw, like it was just more severe. And so I decided to add that in there to see what the difference is. And also, depression and anxiety can progress into PTSD if left untreated. So, and then let me open this. Cool. This is a video of my program running. I decided to speed it up just so it could fit into the presentation. So it takes the file name and it jots that down and then calculates the Formant frequencies, F1 and F2 frequencies of every file, prints that out and logs that to a JSON file, then also plots the data to a graph, which you'll see here. And I also have this on the next screen. And so what it returns is a graph with F1 frequency on the x-axis, F2 frequency on the y-axis, color-coded plots. Blue is for depression, yellow is for control samples, red is for anxiety, and green is for PTSD. And you can see clearly the PTSD samples tend to be on the more extreme end, especially this one. I think specifically this was an officer, a police officer having a PTSD attack. And the depression samples are routinely on the lower end. Control is about, average, a little bit more than the depression samples. The anxiety samples tend to be more extreme than the control and the depression samples. So I think that really returned what I thought would happen. It could be useful in SurveyLex in specifying which trauma disease a patient has. If something registers as anxiety or PTSD, you might want to run this program over it to, specify exactly which one.
Were these, just a quick question there, were these gender controlled, or were they mixed genders, like a male and female?
They were mixed gender. I did an even number for each.
Got you. So yeah, so I'm thinking that might be due to some of the scatteredness as well.
Yeah.
Some genders might have a cluster. You can see, like, for example, there's 3 up there in the green, like light green, not the dark green, but light green, and 3 at the bottom, and that looks kind of like a male-female separation.
Yeah, definitely. I think this was definitely a male, and this one specifically was a female.
Gotcha. Yeah, just a quick comment. But yeah, keep going. Sorry for interrupting.
Oh, you're fine. What I learned from this was a lot about trauma disorders, how it affects people's lives. I learned that not only veterans suffer from PTSD, it can happen from, to regular people, just something, significant has to happen. I learned about writing efficient code, data structures, algorithms, using that to the max. I want to stay involved with NeuroLex and extend the scope of my software demo. I want to optimize my program to run faster and find more data and find ways to make it more precise. I want to continue my work in audio software development, whether it be for analysis or like synthesis. Right now I'm working on a lot of synthesis plugins, like a filter, synthesizer. So I'd like to continue that. I'm looking for, want to close full-time employment. looking for a rec letter. And also in my career development, I gained experience in signal processing and working in healthcare.
Nice.
Here's my LinkedIn contact. Thank you.
Thank you so much. This was awesome. I think the demo really spoke to it. Formant frequencies are something that we've been trying to look at for a while. We haven't really added that into our pipeline at UW, right, Reza?
Does the formants come out of our
original?
No, they're not in like PyAudio analysis.
No. So
how did you implement the formants? Well, did you code it, just manually code it yourself, or did you have a toolkit?
Oh no, they're in PyAudio analysis.
They are, okay. I have to look back and see.
So I think she found it. So that might be good to add in the pipeline.
Yeah, we can add that into our pipeline. And then, what do you think about in terms of with the formants? I mean, how do you think through controlling for like that graph you showed, for example? You know how that you said that police officer with PTSD had the extreme values.
Yeah.
What if he just happens to be like, a 7-foot tall dude with a humongous vocal tract, like how do we control for that? Because like that might change his formant by itself and not reflect the state of his brain, you know what I mean?
Yes, I tried to kind of go off of what I thought would be valid. This one in specifically, he was like clearly in like an anxiety attack. He didn't sound like a big guy either.
Okay, that was off of YouTube?
Yeah.
Okay.
All these are for YouTube.
Yeah. Just thinking through like in the future when we're going to do a bigger data collection, like one thing I try to ask in our surveys if we're doing the collection ourselves, is like because obviously people don't know how long their vocal tracts are, right? But like if it correlates with height, maybe, maybe height is a good thing to ask, or like, I don't know, certain size that people would know offhand, but something to think about, because that'll affect the results.
Yes.
Cool. Yeah, that's pretty interesting. There's a lot of information in formants.
Do you want to continue this afterwards? I guess.
Oh yeah, definitely.
We've been looking at. I think somebody else had a PTSD project as well.
Yeah.
And Reza has been trying to get a PTSD data set from one of our.
I'm working with
colleagues.
Yeah, it's the VA, the Veterans Hospital in Houston, actually sharing some PTSD voice samples with us. So we could, when they send us that data, we could actually extract the formants, and you can take a look at that too.
Nice. Yeah, I come from a military community, so like I'm really interested in working with them specifically.
Awesome.
Cool.
Yeah. So let's definitely get you on that, and hopefully we can kind of do a group paper or something.
Yeah, I think if we just connect you guys. I was telling a person earlier, David Mathai, he's the former tribe member. He's actually a psychiatry training right now. So he's done med school. So he's a little older and he's doing his residency. He's on Slack. You should send him a message, and you can even include me if you want. But David Mathai.
Mathai.
Yeah, Mathai. And just said, be like, hey, this is the work I'm doing, and I heard you're going to have you have PTSD data. He's actually going through and like cleaning it and everything.
Mm-hmm.
So, I can, you're interested in helping extract some data from it. That'd be pretty cool.
Cool. I'll send him a message.
Okay. Yeah, we can definitely continue this.
Cool. Yeah, it really useful too. I think it helped us kind of reflect on formant frequencies, something that we've seen time and time again. We just haven't done it.
Yeah, formants have been important in other voice technology fields, like just translation and whatever. But I think we need to really look into using them more heavily here too.
Yeah.
Cool.
Awesome.
All right, cool.
Really appreciate it. Have a good rest of the day. And then for the rest of the demos, they're videos. So I don't know how best to do this.
Did they post it online? I mean, we don't have to be live anymore.
Yeah, so we're going to close it. So we're going to close out the video now. Thanks for everyone who presented. We're going to kind of do a update on Slack after we watch all the recordings, and take a little bit of time, judge everyone, and then we'll have a post on Slack of the winners, and we'll talk about next steps on that. Yeah. So I really appreciate you being a part of the tribe, everyone, and you, Kamilah, especially. And it's been a really fun journey, and we're really looking forward to growing alongside all you guys.
Same here. Appreciate it.
Take care.
All right.